What's up, everybody? Welcome to Geology. Let's talk rivers and start with the stuff that was in the last video. Hopefully, you check that out. Take it maybe a step further. Excuse me. And we'll really just kind of define like the setup on how rivers work, right? And then we'll get a little bit more into flooding and some different scenarios. So let's just stick to the basics on this one. As mentioned with the other one I showed the river, right? And I said, where does this water come from? You go uphill, obviously, right? Water comes from uphill. And we said that eventually you're going to get to a spot where you're at the highest you can get before you go down. That defines that line would be what a drainage divide is, which is on this line. They call it drainage basin boundary. Divide's the better word to use. That divides out one basin from another. The area of land, and people struggle with this definition. Well, my high school students struggle with this definition all the time. And I think it's just slightly abstract. If I say, what is a watershed? Or same question, what is a drainage basin? The first part of it's got to be it's an area of land. It's whatever like the physical real estate on the planet is that when water hits it, it flows into that stream system. So this Fox River, I don't know if this is real or not. This is just out of your textbook. Would be that every drop of water that lands there is going downhill into this Fox River and out to the ocean, right? I printed off a real one, the Chesapeake drainage basin, which is a really big one. And now people have done a lot of hard work on watershed awareness, particularly in this one, because the health of this bay, both in terms of like fisheries, oysters, just plain old water quality, recreation, all hinges on what everybody in this whole entire area is doing. And this up here in New York, this makes it all the way to Tully, New York. So if you come up from the south, you might know where this is. If you're coming up 81 South, you go by the Tully, there's like a Burger King there or something. If you come up from the south, you're in the Chesapeake Bay watershed. So at that Burger King, it's really pretty close to the line. If you dumped water on the south end of that parking lot, it's going to flow down into the Chesapeake Bay. Whereas if you go north of it, it heads up through the Oswego River into Lake Ontario. And there's actually a sign there now. And if you're on 81, you'll see it's enormous. You'll see now entering the Lake Ontario watershed, because it's wise. It's a growing idea that we should really be like aware of the idea that what we do affects the water quality of that area. There's an enormous amount of chicken farms, especially as you get down into this area over here. And we'll get into like human populations and water quality and things like that. I don't want to get too far ahead of myself here, but consider what you do. Consider even driving around. If you're leaking, as I've had older cars that are barely holding it together. If you're leaking some kind of fluids where you are, that doesn't just disappear. Where you are, it's going to enter part of the watershed. If you're using chemicals and fertilizers, it's now part of the watershed. So that's why you're going to see these signs. And now that I've mentioned it, if you've never seen them before, drive around a bit, you'll see them. Head along the lake, you'll see now entering the Sodus Bay watershed. And it's, again, just to like raise awareness on that, right? So the area of land that contributes to a stream system. The general pattern, I can't say this is a 100% absolute certainty, but it works pretty well. The general pattern is that higher up in the drainage basin tends to be steeper, and then lower down in the drainage basin. And when I say up and down, I'm referring to the way that the water's flowing, not north-south, but uphill, downhill. Uphill tends to be steeper, and as you work your way down, it tends to be flatter. And that's actually what this third diagram right here is showing us. That's closer to A, and that matches this map right here. Closer to A, it's steeper. Your elevation per distance, which we call gradient, how steep something is, it's like slope. Your slope is steeper. And as you get down towards B, it gets flatter. And that's more than just trivia. There's going to be some things that go along with that we got to like get into today, get into the thick of it a little bit. One result is the shape of the channels, where higher up tends to be more narrow channels, lower down tends to be flatter, and that's where you're going to be able to develop these more widely well-developed floodplains. And there you go, hint as to why we're getting into this floodplain, right? We also want to think, you know what you should do? So this will be homework, right? Go to this website right here, copy and paste it, or just type it in. It's cool. if you think this is cool, I think this is cool. You can click anywhere on this map. So I went to my old neighborhood of Tipperary Hill in Syracuse and clicked up here. It just goes to the nearest river, right? So I lived up here. Water flows downhill, and then it'll like, I don't want to do it on YouTube because it might take a few minutes for it to load, but it like flies you downstream. So wherever you live on Earth, if I live here, you pick the spot, it'll run the numbers, it'll figure out where the water flows, and it will like fly you downstream. So play with that a bit. Do it from, it's going to be a little boring if you do it from campus because it just goes into Lake Ontario, right? But do it from home or do it from somewhere you've been and watch how the water flows. The water that comes through the Oswego River comes from our drainage basin is like surprisingly huge if you haven't thought about it. Most of the Finger Lakes all drain to the north and then across right here over towards Syracuse, joining at Three Rivers there. And then water from the south end of the Tug Hill, all of that, like right around between Rome and Oneida Lake is the divide. So water from Oneida Lake also flows in at Three Rivers, it hits, and then out through the Oswego River. So like water from Ithaca's campus and Cornell's campus, actually, if you stand down by the Oswego River, you're watching water that it was a ways ago, was time-wise, but it has made it all the way up through the Oswego River. Whereas water from our campus just right into right, it doesn't make it in up the hill through town and down into the river. It just goes right into the lake. But again, that's that watershed awareness idea. Like how many responsible or irresponsible farms are there in that area? If you go fish in the Oswego River, what has been going on in all of that space that contributes to the health of that fishery? So play with that website a bit. It's cool. But what we also want to think about is that a river is not just water. It's water and sediments. So there's the channel and there's the flow. And I pulled up the webcam. Let's just pull it up again here. I'll pause this quick. So if we pull it up here, you're clearly watching water flow. You can't argue that. But what we'll start to consider is that there's also sediment in this river. It's not just a flow of water. And keeping track of that, understanding that, the nature of that and how erosion and deposition takes place is going to relate to floods. I'm not doing this just to like babble about rivers, although I enjoy that. We're doing this to consider how that might lead to flooding or how changes in that due to human interactions may lead to flooding. So back to it. The golden rule. This is going to cover you. We're going to talk about a couple scenarios here. And it all is this. I'm going to say basically the same thing a couple of times. The idea is that if water speeds up, one reason or another, faster water is going to lead to erosion. Whereas slower water is going to lead to deposition. I'm even going to spell it right. Should I probably say of sediment? We're talking about the sediment now, right? So erosion of sediment or deposition of sediment. The movement of the sediment if it's eroding, or the drop-off of the sediment if it's depositing. So as you sit there and watch that, some sand, silt, and clay from upstream is part of this river system. Where, as it flows, is it going to have places where it either speeds up or slows down? There's other ones on this page, matter of fact. There's a little further downstream. Where are the places where it speeds up? And when it speeds up, just picture it. If you were to go take a little cup of sand and put it right in this current right here, it's going to wash its way downstream. But there's going to be places downstream, certainly by the time you get to Lake Ontario, where it slows down enough where that sediment can't be supported by the current anymore, and therefore it will get dropped off. So one quick moment. Let me pause. Right, so like this graph right here, don't be intimidated by it. It's not that bad. If it looks scary, it's not that bad. Tells us that relationship. This curve right here would be where the answer is, right? So if my stream velocity, if it's going this speed, anywhere here on the x-axis, if you go up to where it hits that black line, it can move particles of that size. If you've never seen it before, the way we categorize particles is by their size: boulders, cobbles, pebbles, sand, silt, clay. Those are like official names. I'm not making those up. And water going this speed will carry those. So you can you can kind of deduce this idea here about our golden rule from this graph. Because what happens if the water is going, let's say, 50 centimeters per second? And maybe I'll put a question with this little graph on there. So if you're watching this video, I do appreciate it. And hold on to this, have this open for the quiz. So yeah, let's say it's going 50. So it can carry about this size pebble, right? A little bit smaller than a centimeter. If it slows down to 10 for some reason, and whatever reason it could be, maybe the river gets wider, maybe the river gets flatter. If it goes down to 10, now it can only carry particles that are this size, about 0.2 centimeters. So what happens to all those ones that it was carrying at the faster speed and now can't carry anymore? Well, they get dropped off. So what you end up with is a nice, neat, sorted, organized pile of exactly that size sediments. And then if it slows down further, it'll drop off some different sizes. Running water, as it turns out, and whether it be rivers or waves or wind, is very good at organizing sediments. You want to do a little quick experiment with that and have a nice afternoon safely, go down to the beach in front of the new campus area, down towards the west side. And if you walk along it, you're going to find all cobbles that are a very consistent size. They're very well organized. What did it? And maybe this time of year when the ice is just leaving, it'll be a little bit jumbled up because ice is a disorganizer. But once the running water takes over as we get more and more into summer, very well organized, like almost miraculously. If you really just sit there and think about it for a minute, it's like, who sorted all these out? Well, nobody did it. That's what running water does. It's very good at organizing particles. Because of this curve right here, nothing happens instantaneously other than the ice, right? The ice would be the thing that just, it's a big bully. It picks everything up, dumps everything, and mixes it all up. So, speaking of not babbling about rivers, what else we got? So, like higher up in rivers, and the kind of sticking with this idea, I stole this from the web, but this is when I lived out west, up south of Nederland, Colorado, or not south, downstream of Nederland, Colorado. This remarkable canyon. I mean, if you're in a little car right here, these walls are huge. So this would be high in a drainage basin. The divide wasn't that far upstream, the Continental Divide. So fast flowing water is good at erosion. So it tends to cut its way down pretty quickly, and you get these deep V-shaped valleys. Now, you got to keep that in mind. I'm not going to get into the flooding today, but when we get into the flooding, that means that there's a specific kind of flooding that may happen here that's more likely here than it would be downstream in the flatter areas. Get down to the flatter areas, and that's where you're going to have, instead of like cutting down, you get more like side to side, and this floodplain can develop. You get depositional environments too, because this is a very erosive environment. You're eroding your way down into this tight V-shaped valley. All that stuff's got to end up somewhere. So it ends up in depositional environments where the water slows down, like deltas, like the end of Mississippi River, or alluvial fans here, wherever that is from your text. All right, so let's go that golden rule again and think about what happens when it gets flatter, when we stop cutting into the crust as quickly and we start having what we call these meandering streams, which it doesn't look like it says anywhere. And that term, it's likely to pop up, honestly. Meandering, if you know what it means to like meander, if you meander to your next class, you go see somebody, then you go grab a coffee, and then you do this and you do that. You take your time versus straight line, right? That's meandering. Rivers will do that too. And especially, and will certainly, only when the floodplain and when the gradient, when the slope gets to be lower. You're not going to see a meandering stream coming down a steep hill. Just water goes down, right? So this upper section of the drainage basins tends to be more dominated by the straight streams, when the lower section tends to be more dominated by the wide floodplains and meandering streams. But again, we're going to have the same rule pop up. When water's flowing through one of these streams, and there's a really good, very basic Minute Earth video. It's a little series that shows this with better animations than I could possibly draw. What happens is that as water's flowing through one of these curves, it ends up going faster on the outside. It like pounds into the outside, and then works its way back over here. So the result is that on the outsides of bends, you get faster water. Golden rule, don't forget it. Faster water means erosion. What's going to happen is that that bank is actually going to get eroded away, and the river's going to want to migrate that way. Whereas on the inside over here, you get slower water. And again, go back up to that golden rule. That's a thing. You're going to get deposition. So here it is. I'm going to pop over to Google Earth too, and we'll check it out. That you get what they call cut banks on the outside because of the faster water, point bars on the inside because of the slower water. And through time, these curves will get bigger and bigger and bigger. And in fact, they can get so big that they like cut themselves right off and almost re-straighten again, leaving you with this separate thing we call an oxbow lake. They are very spottable in Google Earth. So I went to this. This is just, here's roughly where we are. And you can even see, and this is due to farming, right? But you can see the color difference on what we would say the floodplain is versus the steeper parts on the sides. You can see the rivers being more straight over here and more meandery over here. You can see towards the insides of many of these banks that that's where we get sand. All right, especially on the smaller guy right here. Come on, focus. There we go. Outsides, cut banks, insides, point bar. So the water's faster on the outside, faster on the outside, faster on the outside. It will make these meanders bigger and bigger and bigger. And you can see that's like called a meander scar. You can see where older rivers or Oxbow Lake, older channels have been before they get cut off. You can even occasionally, if you get lucky, and I don't know how much I want to search for this, you can see where trees on the outside fall in because of the erosion on the outside. But I don't want to take all day looking for that, right? Now they can be big. This Oxbow Lake right down here, just to give perspective on it, I mean, here's a town. Sorry, my internet's going so slow today. But there's a whole town here. If this thing doesn't wake up, I'm just going to skip it. But you can see, kind of just get some perspective on how big this Oxbow Lake would be given that town. So there's like boating docks here. I mean, people, consider the size of that. It's relative to the size of the channel, of course, right? But it's not to say like Oxbow Lake's got to be these tiny little insignificant features. That's a big thing. And I love this one because you can even see in the soil all of the buildup that would have been that bar as it built and built and built and built and built its way out until this curve got bigger and bigger and bigger and bigger. But eventually the curve gets so big, so sinuous, that it gets cut off. The active channel goes through there. The separate thing becomes our Oxbow Lake. Cool. All right. I'm also going to, at times, I don't know if we have anything else. And this is just other examples of it from your book, although I don't know. I think I like the Google Earth shot better. I'm going to at times bring up, and maybe on the quiz. I used to have it on the quiz. We'll see if I pull it off again. Chittenango Creek. Now, I used to teach at Chittenango High School, which is right in this town right here, if anybody's familiar with it. But it's just a good type section for being fairly close to Oswego for a difference between a more quickly flowing stream. As you go from Cazenovia down to Chittenango, you go down a pretty decent amount of elevation. Town here is at about 1214. Town here at 517. So that's a pretty good downhill. And it's a very nice drive if you've got the time to go do it. And there's a great big waterfall over here, a state park, Chittenango Falls State Park. That's great. So maybe I won't say exactly what I'm going to put on the test, but consider the things we talked about, right? If this is the part that's steeper, this is coming down from the plateau part of the state, the Allegheny Plateau. This river flows north. It can happen. Flows north from Cazenovia down this steep hill into the town of Chittenango. Down that was like 700-ish feet. But then, and you can see I've got it highlighted for some other things I did. That's what that white line is over there. Then from Chittenango at about that 500 feet to where it leaves to Oneida Lake is at almost 400 feet. It only goes down about 100 feet, that whole distance. So they're kind of reasonably equal distances. Over that much you go down 700 feet. Over that much you go down about 100 feet. what is that going to be in terms of the shapes of the rivers, where you're most likely to see meanders and oxbow lakes? And then to come in the next video, what kind of flooding would you get as a result of those two different environments, right? And it really kind of shakes down to like this little hypothetical or real, I don't know, drawing where Casnovia could be higher up, Chittenden goes about halfway, and then its exit into Oneida Lake is down here on this flatter part. All right. Lastly, the reason why the Egyptians were so successful for thousands of years, and this part of the United States is so successfully farmed, though maybe not as sustainably, is because floods have like what your book refers to as a natural service function. What comes out of these disasters, and it's easiest with floods, I think, that is of use, that is of service to like how we see the planet. Well, the flood deposits tend to be very fertile. They're coming from river. They're chock full of life, right? Decomposing, whatever, natural fertilizers that when there's a flood and it drops its sediment over that plain, because, hey, there's our golden rule again. If it's constricted to the channel, it's going a certain speed. But when it floods and fills that whole valley, yes, there's more water, but it'd be a significantly wider channel. It's going to have places where it's slow and it will drop its sediment. And then it will settle into a new drainage, channel, a new river channel, and leave behind all of that very fertile soil. So that is why, back to Google Earth, that this area of the country has such significant farming, because of the soil through there is very, very fertile because of years and years and years pre-human, that floodplain getting well developed and filling with wonderful, delicious farmable soils. So we'll have to get into a little bit on how our practices have maybe monkeyed some of that up a little bit, but we'll get there. I think we've probably talked long enough about rivers for now. So we'll talk about how we get different kinds of floods in those, and then a little bit on how humans can change the nature of drainage basins and change the nature of how quickly water flows out, which I think I alluded to in the last video, right? With like that Great Northern Mall area, how much that's blown up. So what is a water droplet to do if before it used to land in the woods and now it lands on a piece of asphalt? Thanks for tuning in, and we will talk to you soon. And I will now awkwardly try to find that stop button again. There it is. So long, everybody.